Okay,
Yep.
let me share a screen with the book. And yeah, so this time we've got planning and learning with tabular methods, and this is the last chapter in the tabular methods section. And here we will discover how the planning can be incorporated into our learning framework we saw so far. And the planning part relies on a model. So here, let's first define what in this case the model would be. And here in book, it's said that the model is essentially anything that takes a state and an action and produces how the environment will respond to the action. So in this case, we are talking like not about all the things that model can be in general, but about particular thing. So when we are talking about model-based reinforcement learning, we are talking about the reinforcement learning when we use a model of the environment, right? So basically the term model refers to many different things, but in this case, we are particularly interested in the usage of the model of the environment. Okay, and there are two possible kinds of models. So one is distribution models, and that would be a model which, given a state and an action, or so a state and an action will output a probability distribution over all possible future, like not future, but next steps, states and rewards. And another kind of model is sample models. And this is the kind of model which, given a state and an action, will output one possible state and reward from space of possible states and rewards. And obviously distribution models are more powerful, but in many cases it's much easier to get a sample model, but it might be like really hard with respect to computation or amount of data you need to get a good distribution model. So that is why both of this appear in different contexts depending on what are the constraints we have, right? And like an example of this is given by here. So here for blackjack, it's really easy to get a sample model, but a distribution model would be harder to get. And I think it's definitely applicable to all the kinds of card games and many similar applications when we have kind of well-defined but complex behavior, right? So what is planning in this case referred to? So in this particular application, the term planning refers to when we use a model to sample the possible outcomes for our states and actions, and use those, and we use those outputs from the model to improve our policy, for example, by learning a state value function or action value function, right? And yeah, there are two approaches to planning, basically in two classes of approaches, but we will be dealing only with one of those, and that's state space planning, and it's contrasted to plan space planning, where we are searching in a basically in variety of possible plans we can have to how to move through our or how to behave, right? And in this case, we are just trying to improve our estimates for for a value function we have, right? And in this case, the planning actually is very similar to learning, and we will see that in a diagram really soon. So so here is some simple algorithm for random sample one-step tabular queue planning, and it should help us to relate planning to the learning algorithm we considered before. So what would we do during planning? So each step would be we select some state and an action at random, and then we just use our environment model to obtain the next reward and a state. So in this case, it's just like the very beginning of the learning process, right? But instead of observing actual rewards and getting into the actual next state as determined by the environment, we are getting these values from the model of the environment, and then we do an update, and this is a regular queue learning update here, and yeah, essentially you can imagine any kind of update rules applied here from those we considered before, depending on what what we want to use. The essence would be the same. So the only essential difference here between planning and learning is in that we are using a model of the environment instead of learning from actual experience. So to summarize, learning happens from experiences, and planning is kind of the same process, but which relies on the model of the environment, which is in turn also probably it is learned, but that's another orthogonal kind of scene. Yeah.
Yep. So in this, only planning is performed, or both planning and learning?
Excuse me, could you repeat it?
In this algorithm, the random sample one-step tabular queue planning, is the planning step only performed, or the planning and learning part? The combination of planning and learning part?
Well, given the definition So if we assume that learning is something that happens from the actual experiences, and planning is what happens based on the samples from the model or outputs from the model, then it is just planning. But actually you can see that it basically depends on how you define a learning. So we do update the action value function, right? And at each state of planning, our action value function will change. And yeah, so in other words, we do learn action value function, but yeah, here, like according to the terminology, this is called planning, right? So we kind of plan our action value function, if you would, but yeah, that's kind of a bit maybe confusing, but that's how the things are defined. And maybe when we look at the Dyna algorithm, it will be kind of, so here is this direct reinforcement learning step, which is kind of, so we can define learning either as all this process combining everything, or as or particular as what happens from real experiences. So here in this direct reinforcement learning. And here is another path that refers to planning, but let's just unroll it and see what everything means. So here are two, so we have a certain value function and some policy, which is probably defined by the value function, right? And we act according to this policy, we get the experience. And from that experience, we can directly learn the state value or action value or whatever value function and the policy. And that would be, so this loop is what we considered in all our, in all of the previous chapters, right? So we, you can see that this loop is kind of generalization of what we saw before. We get the experiences, we update the value function, and then we use it to get more experiences, right? And here is another loop. And this loop is the planning loop, we can say. So here we use our experiences to learn a model of the environment. And then we use the model to do the same, to update the value function and the policy. But in this case, you see that we use the experience to update a model, and then we use model to kind of update the value function. And what is the benefit of having this outer loop? Like, so the benefit is that we can do multiple, like getting actual experiences can be costly. And by learning a model, we can do multiple updates to our value function and policy in between the actual experiences, right? So we can, when we have a good model of the environment, we can learn a lot without actually interacting with the real environment. So that is what planning is for here.
So
right?
Here there will be the simulated experiences based on the simulated experiences from the model. The planning will be performed, right? And if I try to make an arc here, this will be the real experience from which we have the direct RL, and this will be the simulated. experience. So this will be the difference, I think so, between the two cases.
Yeah, and so this path, which we can call learning, or more precisely direct reinforcement learning, and this path we call planning, right? So that's just naming convention we use in the future.
Cool.
And here you see that it can also be called like indirect reinforcement learning. So that would be the same as planning, right? Okay, and
The
just
indirect reinforcement learning is the imitation learning, if I'm not wrong. Or that's the inverse reinforcement learning. The imitation learning part, is it the indirect reinforcement learning, or was it called the inverse reinforcement learning?
Yeah, probably that's kind of just different ways to name different things, and sometimes different things are called the same way. So here you see that like improving a value function and policy based like indirectly via the model, sometimes called indirect reinforcement learning, but yeah, sometimes maybe some other thing is called indirect reinforcement learning, and sometimes this thing is not called indirect reinforcement learning. So we shouldn't probably like
I got you. Yeah.
Terminology too much. I think that so the main idea here is that we use the state transitions outputted by the model of the environment, and then it is planning, or in other words, it is indirect because we do not directly interact with the environment. Instead, we just use our model for to generate the experiences, right? And yeah, so I think the best and the most like clear is way to understand it is to read the algorithm. So let's do that. So what would we do? So we will initialize our action value function, and we start with some state and action. So that's what we are usually doing for any kind of methods we discussed before, right? And also we have a model here. So that is something new. And now we do just as we did for example, Q learning, right? We take our state, we select an action according to our policy, given a state and our action value function. Then we take an action and observe a reward and a state. So this is an interaction with actual environment, right? And we do the update here. It's Q learning update as usual. So this A to D steps are like actual Q learning algorithm as we learned before. And now here we have two new steps. We assign, we use this new reward and the state to update our model. And after that, we do kind of n planning updates. So here this loop will be this planning loop we saw before. Let me just scroll to it. So we do this in another kind of inner loop, right? We iterate that. Sorry. iterate that loop multiple times, whatever number we choose. And we sample a state, we select a random action, and then we feed this state and action to the model, and we observe the output of the model, and we use it for the same Q learning update as here, right? But this time we are using the reward and the next state outputted by the model, not by actual environment. This is not an experience from actual environment, right? And here a thing to notice is that we can only use previously observed states and previously observed actions, because our model here in this particular case makes no sense for the states and actions we didn't observe, right? So if we don't have an experience and real experience for this state action pair, it is not useful to update our action value function by using the outputs of the model for that state action pair, because it is not meaningful. The model output is not meaningful in that case. And you can imagine probably a different scenario when our model is given, right? And maybe we will update it to improve it, but it could encode some prior knowledge about the environment. And in that case, we can kind of release this restriction on using only observed state and actions, right? So, but yeah, that's just a speculation, and probably we will interact with this more in the future. So
yep. I had a comment here with respect to, suppose, combining the simulated experience versus the real experience that we get to take the update from the tabular DynaQueue. I think so they are also combining it with respect to the queue updates that they are doing. Here they are using a simple this. If I try to make this guy here, this is the sample update which they are doing to update the queue values of the state and action pairs. I was thinking in terms of the simulated experiences and the real experiences that the model has, and how do we combine them in the DynaQueue?
So this is a real experience, right? So this is update done using a real experience. And this update is, we use the same equation here, right? So we do the same kind of update. You can see that everything just matches. But here we use a reward and a state outputted by a model. So as you can presume from this, that when doing this update, we assume that our model is good, right? And probably there are some, one can use some heuristics to kind of schedule this update. So probably like in some cases, when your model is really bad, it doesn't make much sense to run n steps of planning. But on the other hand, in some in some applications, probably it is always best to use all the time you have for planning, because like when you like basically have a free compute, right, and the time between your actual experiences is large here, and you just have some time to spend, and you can do this updates. And probably this is really dependent on the particular application, and I hope we will get a more knowledge of this when we consider different examples and different scenarios when this approach is used, right?
Yep.
And yeah, so let's have a look at a very simple example to start with. We have a simple maze here, and here we have this learning like curves. So y-axis is steps per episode, and obviously, like the minimal number of steps to complete the episode is given by this kind of path here, right? It would take it, or equivalently, we can go this. Probably this one is longer, right? Okay, so that is our best path we hope to learn, right? And you can see here that it kind of comes to this 14 steps. So that's a minimal possible number of steps. And you see some like variation here because we are using epsilon greedy policy. And okay, and you can see that the more planning steps we do, the faster we get to the good solution, right? So the good solution here is this 14 steps getting to the goal. And why does it happen? Because let me get it back to remove this one. Okay, so here we can here is a figure showing kind of which for which states we have a meaningful policy here. And you can see here that when not using planning, after the first episode, we only update the state that is prior to the goal state, right? So everywhere here, the reward was 0, and our initial estimate for the action value function is 0. So no, we gain no information for any states that we visited before getting to the goal, right? Only the one step before. And we saw this problem in previous chapter when we discussed n-step bootstrapping, and here it is kind of the same. So we need to propagate the information like 2 steps away from the goal state. We got to do like we got to experience 2 episodes, and that is obviously not very data efficient for many use cases, right? And here with 50 planning steps, we are actually getting this bunch of updates here for like 50 steps that took us or not 50 steps, but now we can kind of propagate back this knowledge in 50 simulated episodes. And we can do that for all the states we visited during the first episode, right? So we will select at random 50 states, right? And we will update their action values based on this first episode we experienced. And this will kind of randomly propagate this one state which we updated, so the information that was used to update this one state, which we updated during actual interaction with the environment, will propagate it to a bunch of previous states visited during the first episode. Okay, and here is the question. So the non-planning method looks particularly poor in figure 8.3 because it is one-step method. So multi-step bootstrapping would do better. And do you think one of the multi-step bootstrapping methods from chapter 7 could do as well as Dyna method? And yeah, so that is the question. And what do you think about it? So my understanding is that if we do like this, for example, 50-step bootstrapping here, we will also update 50 previous, like all the 50 steps that preceded the terminal state, right? And that would be, in some sense, very similar to the planning, right?
Mm-hmm. Yeah.
And yeah, I'm not sure if there is some benefit to either of these methods. So that is kind of, it seems to me that both methods will result in similar performance here. For example, you can notice that for this particular state, like the bottom right corner here, we have a run kind of wrong direction, right? But that is probably because the action we sampled it for this state, we never kind of checked what would happen if we go this way, right? And that will like in a limit we will check that action as well and update that state as well. And kind of the same is true for the TD update and step bootstrapping with unstep bootstrapping, right? So if yeah, so this particular pattern probably won't be possible, or maybe it would. I don't know. Yeah, it could be possible. So if we went in some kind of loop,
exploration might be the issue here.
Loop here.
The number of exploration steps might be an issue here. I think so. In the next part, when we come up across DynaQueue plus method, then that will give us a better overview of the updates that can be done in the grid world. And there, I think so, the arrows or the actions will be chosen corresponding to the exploration of a particular, how do I say it, the grid here, in which direction the particular agent has to go. So there, that issue might be assuaged there. In that case, in the case of where the exploration is given a bit of a benefit.
Yeah, probably that is relevant. And okay, let's in this case, let's move to the next examples. And yeah, let's explore this blocking maze example. And it will show us some limitations of DynaQueue and a way how can we try to improve it. So in this problem, we do 1,000 steps in this kind of grid world, and after 1,000 steps, the path changes. So before we had this like shortest path opened for us, and after 1,000 steps, the shortest path is closed, and we got to go around this wall to get to the goal state. And in this kind of problem here, what
So
we will
you mean on the left hand side, the 1,000 steps are using this.
Yeah.
Okay, and on the right hand side, okay. Yeah.
Yeah. So for the first 1,000 steps, we can go this way, but after that, the path is blocked, and we got to find another way. So and that is why probably if we could like really look very closely to this graph, so probably you can see that here the slope is kind of higher than here, right? And that is because the like cumulative reward per step will be lower because our path is longer. And yeah, so so let's have a look at what DynaQueue Plus is. And first let's think about the motivation here, right? So when this path is blocked and we are using DynaQueue, so during training we will still be kind of stuck to this information here that we can like all our Q values are learned in this world, and they kind of tell us go this way, right? And after kind of this path is blocked, we spent a lot of time still trying to kind of go that way, but it is blocked and we can't. And somehow after kind of tons of experience, we will learn to go a new way. But can we switch faster? And a DynaQueue Plus is one of the ways to kind of encourage the exploration of states that was not visited for some time. So yeah, let's kind of fix this point here, that with regular DynaQueue, we assume value of this state that leads us to the new best path. We assume it to be low because it was really low under this kind of world, grid world, right? And the DynaQueue kind of artificially bumps up our estimate for the Q value of this state. For example, because if it was not visited in a in our real world experiences for a while, so it kind of encourages exploitation by making our state action estimates for the states that were not visited for a while higher. And precisely this is done by so during the planning stage we introduce this bonus reward, right? And the bonus reward will be proportional to the square root of the number of steps so the tau here, time steps. So this is number of time steps. We did not visit that particular state in the real environment, right? And so we will add some constant k here, is a small constant, and times the square root of the number of time steps we did not visit that state. Okay, so let's look at another example where the DynaQueue is particularly beneficial. And here we have another transformation, like change in the world. We get this shortcut. So for first, for first 3,000 steps, we don't have this path here, the short path. We got to learn this longer path, right? And after 3,000 time steps, the shortcut is opened, and you can see that the slope of DynaQueue does not change, which means we are in this new environment. We are still going this way, right? Because we already learned that the values associated with all these states is low, and that is why so we need a really long sequence of exploratory steps to find this new path here, right? So it would be like, imagine that we should our greedy policy points us in this direction, so we will have to do like 1, 2, 3, 5, 6, 7, 8 exploratory steps, 8 consecutive exploratory steps to get here and to find this new shorter path. But as we do this exploratory steps with fixed probability, and that probability is really low. It's like regularly we use epsilon of 0.1, right? So that is almost impossible that we will take that we will find this path with a regular DynaQueue. But with DynaQueue Plus, after each real world episode, we do not visit all these states here. They're kind of the planning update for this state gets a bonus reward, and eventually we will bump the action value function for these states high enough so that we will go to explore this region and we will find this path. And after that, you can see that the agent always exploits this new better path, or often exploits this new better path in DynaQueue algorithm. So that is interesting, and that is one way to do this exploration in planning, right? So okay, so let's check the exercises. So we say that why did the DynaQ agent with exploring performed better in the first phase, as well as the second phase in the blocking and shortcut experiments. And yeah, let us think about it. So probably the regular DynaQ agent, the first pass the agent took to get to the goal state, it's unlikely that that was an optimal path, right? And but with DynaQueue, we use the values associated with that path to update it for n planning steps. And probably we were still using kind of the states we already visited too often. So we have this kind of maximization bias, right? We discussed it during the previous session, and probably this maximization bias leads us in some suboptimal way, and the DynaQueue plus algorithm will kind of force us to explore the states near that suboptimal way and to kind of improve it faster than the regular DynaQueue algorithm. So
plus on the bottom of the 168 page, there is a if you turn to the next page,
yeah,
underneath this prioritized sweeping, yep, here they have given in the subtext the DynaQueue plus agent
okay,
was changed in two ways as well.
Yeah. So this I got it. So this changes relevant to the DynaQueue agent, right? So as we kind of discussed, so the DynaQueue only updates the states that we already visited, right? So if during the first episode we did not, for example, visit this state, or for I don't know, some kind of so still in this particular problem, it is a bit weird that we have this kind of problem, because I think that we should visit at least once all the states that can give us an optimal path here to get to the goal state, right?
Yep. I think so. After and the goal has been reached, then they are giving rewards or some sort of a bonus. That's the exploration bonus that we looked at to the states that were not visited. So that's why in the planning phase, after the model has been made, in the planning phase, those exploration of the catered states are being done. So that's the reason why I think so it's dynamically changing.
Yeah, so here, like, just to summarize this changes to DynaQueue plus algorithm. So first we can consider the actions during planning that never were visited during our actual experiences, and the model is initialized in a way that all the unexplored actions lead back to the same state and give us a zero reward, right?
Yep, that's also beneficial as well when we look at from the unexplored state point of view.
Yeah, and
there is no negative reward, so everything will fall back to zero. So it will try to explore more, since there is no cumulative penalty on the additional exploration that we got.
Yeah, true. So most of the transitions like give us 0 reward, right, by default. And yeah, that's a good point. So here, the next exercise, that the difference between DynaQueue Plus and DynaQueue narrow slightly over the first part of the experiment. And the question is, what is the reason for that? And I think it is kind of obvious that the reason is that, like, over time, DynaQueue enforces us to explore the states that are not really good here. So the same factor that was responsible for us finding a new path, it is responsible for the fact that when the environment is static, the DynaQueue basically catches up with DynaQueue Plus because of those exploratory. DynaQueue basically takes more exploration and less exploitation, right? And when the environment is static, all we need to do is to exploit, right? And the balance between exploration and exploitation is more towards exploration in DynaQueue Plus than in regular DynaQueue. In regular DynaQueue, the exploration comes only from epsilon greedy strategy or policy. But in DynaQueue Plus, we have this another way to enforce exploration. And that is the cost we pay. So that we lose some of the reward here. And probably if we run for long enough, the DynaQueue will outperform DynaQueue Plus, right? Okay, so the next exercise is supposed to be programming exercise. And what would happen if we, instead of introducing this bonus reward, we will just use this, we will store the like tau values for this state action pairs, and then we will use those as a like addition to the action value function when selecting an action, and that will result in slightly different algorithm, but yeah, I haven't looked at this yet. And the next question, how might the tabular DynaQueue algorithm be modified to handle stochastic environments? And how might this modification perform poorly on changing environments such as considered in this section? And could the algorithm be modified to handle stochastic environments and changing environments? So about stochastic environment, instead of learning like a single possible transition, we should, I think for stochastic environment, we should modify our model to count let's go back to the box with the algorithm here. And you can see that when updating the model here, we just set the value for state and action pair to be the observed reward and state, right? And in this case, with each of the real experiences, we just overwrite the state action value for the model. But if we have a stochastic environment, what we should do instead, we should count the times we took an action A from state S and then we should kind of record the outcomes and weight these outcomes by the counts. And in that way, we will be able to probabilistically sample the reward and the state using this kind of
MDP, we can say.
Yeah, and another thing here, so that would require a lot more memory. So we are kind of effectively trying to remember all the possible outcomes. But in the case, if our rewards are not kind of also not integer rewards as considered here, but we can have some continuous rewards, right? And in that case, we probably want to average over the rewards, and for example, for each transition, we will store the average of the rewards, right? And that is another possibility. And in expectations, that would be the same as storing all the rewards. But that would be more memory efficient in case, for example, in the case when we have a lot of possible values for the reward here. But when we have only few possible values for the reward, it probably not that important. So that in that case, we can store all the state and reward pairs we observed, right?
Or there might be some updations based on the Gaussian policy or some other sort of a policy update in which we might have some stochastic environment in which some sort of a noise might be inserted, and we might have to choose the best possible sample distribution of a action given distribution, Gaussian policy or something, and then we might
also,
have
if you
to
remember
apply some
this upper confidence bound, for example, algorithm we discussed in the one of the very first chapters, right? So that is a way to deal with kind of lacking experience, right? So we, for example, we can also take into account how much information we have for the estimate of that particular state action pair, right? And if you watched this David Silver's lecture, he also mentions that there is a Bayesian approach to this kind of, so we can try to learn a Bayesian model instead of kind of regular maximum likelihood model, and that will kind of so when we need to take into account how confident are we in that particular model output, right?
Yep, true. I agree on it.
Yeah, and also to account for the change in environment, we can basically try to use DynaQueue as well, right? DynaQueue Plus as well, I think. And another thing we probably need to do to account for change in environment, that so when averaging the rewards, as discussed before, right? So we store the average of the reward, but we might want to do some kind of exponentially moving average instead of the full average, right? Because we want to kind of forget the very old rewards, because those might be not like not representative anymore, right? So instead of doing the kind of average over our all experiences, we can use some kind of momentum to to remember, effectively remember n latest experiences, right? And the exponentially moving average is a way to achieve that without increasing the memory requirement for that process, right? And this probably the same with the counts. So we want our counts to be not kind of all lifetime counts, but we might want to, for each transition, we want to have like this exponentially moving average of the probability, like of a normalized count, right?
Hmm. Yep, totally agree. And the type of memory, I think so, they have DynaQueue paper too, which in which they have uh, a transient and a permanent memory, in which they try to do a similar sort of updates with respect to the environment transition dynamics. And I think so that was a paper in 2008 ICML, which David Silver and Sutton wrote. So I think so that too also works. I do not know if they have given a reference to this paper.
Yeah, if
Uh,
you can post it in on the Slack, it would be nice, and we can discuss it next time we meet.
yeah,
So
cool.
cool. Yeah. Okay. So we kind of with that I think we covered in most general terms the ideas related to DynaQueue and DynaQueue Plus. And so the next way to make our algorithm more kind of compute efficient is prioritized sweeping. So imagine a really large state space. And if we do these updates during planning at random, we can end up really not achieving much, because we will do a lot of updates for the states we actually never want to visit under, or we will never visit under our current policy, right? And so that in that way we will kind of waste a lot of compute. But to improve on that, there is an idea called prioritized sweeping, right? And in that case, what we want to do is we want to start focusing backward from the goal state, right? So the most relevant states we want to update are the states that lead us to the goal state, right? And but by working backward from this goal state, we can focus our updates on those which are the most interesting for us, right? And here is this algorithm. Let's have a look. So we have this kind of so this is a difference between yeah. So updating the, or I think I got it a bit wrong. So talking about the large state space only, but also we are trying to take into account the fact that the update to the states which are really far from our goal states are less informative. So at some point we will because of discounting, right? So we will get to the point where our update is not really like is really small. So that is why we are going to prioritize the update by its magnitude, right? So here we have some threshold theta, and if the so here you can see this is kind of our error. So a difference between the observed reward and kind of our expected returns minus the previous estimate. So this value kind of shows us how much do we want to update our so how significant this update would be. And if it is larger than some threshold here, we will insert it into the priority queue with priority proportional to the magnitude of the update. And then we will loop over we will loop through this priority queue. And in this way, we will update not 50, for example, say we have 10 planning steps for each step we take in the real world. And before, with DynaQueue, we would update like 10 random state action pairs from our previous experiences. But here we will update 10 state action pairs which are associated with the highest or largest change we want to make to the Q value of that state, right? And we have this.
Yeah.
Go
on. This is kind of like the effects of the changes are propagated backwards until it has reached the end of the loop.
Yeah. So in this grid world example, we can kind of reason about it on an example. Let's try that. So here, all the differences, like consider the first episode, right? The differences between this one, like any state here and here, in real world experience would be 0 because the update, like our initial estimates are 0, and so initialization for action value function are 0, and the reward is 0, so the update is 0 as well, right? And it makes no sense to use so we will record that into our model of our environment, right? So we know that the transition to the right from this particular state will lead to the 0 reward, and therefore 0 update to our action value function. But the transition to the goal state will lead to a large update. So we had the estimate here equal to 0, but now it is equal to 1, right? So because that is a terminal state, and we want to focus on the updates associated with that high update. And what we will do, we will insert it into the priority queue here with the priority 1, and all other transitions were inserted with priority 0, right? And after that, when we update this state, we will look at all the states that lead to that state, and we will insert the updates associated with updating the previous state with respect to the newly updated state into the priority queue. And in that case, this second previous step will be inserted into the priority queue with a priority of 1 multiplied by the how it's called, the gamma, the discounting factor, right? And that is why it will be updated. Updated during planning before all the meaningless updates. We will not try that, right? And that is what the prioritized sweeping will do for us, right? So here you can see that after we update the highest priority state here, we will loop over all the states that lead to the state S, the one that got the highest update, right? And and we will set the priorities according to this newly updated difference, right? And our predicted reward, for the example we considered before, our predicted reward is still 0, but this component is high, right? Because we updated the action value function for the next state with a high reward coming from the goal state, and that is why it will be inserted into the priority queue. And then once we inserted all the previous states into priority queue, again we will update the next highest priority state that will be second next before the goal state. So that, and when we go kind of deeper into the training, that dynamics will change a bit. And here you can see the comparison of updates we need to make before we reach the optimal solution. And depending on the grid world size, and you can see that kind of for small grid worlds, the prioritized sweeping works much better, but at some point it kind of gets with growth of the grid world size, we kind of lose this how it's called a benefit we get from the prioritized sweeping a bit. So that is interesting. Okay, and yeah, so there is another example for describing a road manuring and showing that how it can be how it can be useful to use that prioritized sweeping for this kind of problem. Okay, so that is
one drawback of prioritized sweeping that I can see is that it gives urgency to the values that have the maximum change. So if in the previous steps, if the value has changed the maximum, then in the next steps, that change would be given the priority. And this, I think so. That's the reason why it kind of like the difference between the DynaQueue and the prioritized sweeping. That's the difference. I think so. Why it hasn't been able to overtake DynaQueue on this type of grid world environment, because and the changes might be less prominent after a couple of updates. And if we are giving the priority to the same, that might have some sort of issue in trying to detect the next change that has to be given the priority, so that it changes more frequently as opposed to the previous changes that had the maximum amount of change some 5 or 6 steps back. So that might be the case too.
Maybe interesting. Yeah, I'm not so sure why why we observe this nonlinear kind of dynamics here, but yeah, that is so. Yeah, a thing to notice that this is a logarithmic curve, right? So, but still, yeah, we don't need to expect this kind of improvement to be linear in any way, right? Because the number of possible possibilities, like with the size of the world, it grows really fast. Okay. So the next topic to discuss is expected updates versus sample updates, right? So there are, as we encountered before, there is a lot of different approaches to the updates, and they are different in terms of whether we are using samples or we are using the expectation. And so let's have a look at this kind of figure here that gives us a really good summary of what the differences are in terms of expectation and the value we are going to estimate. So first, we are trying to estimate the value under policy pi of state S, and we have 2 examples here. So one step temporal difference update will be a sample update, right? So we take a particular transition. So we take an action A and we consider a transition to S prime associated with that action and reward associated with that action. So that is a sample. And we are trying to estimate the value function, state value function given a like under given policy. And the dynamic programming update for the for policy evaluation, that what I think we have looked at this in chapter 4, right? Or yeah, was it? It was chapter 4 or chapter 3? Yeah. Oh. Yeah. So sorry, I've switched. Okay. And so for dynamic programming, we are using expected updates. So we consider all the possible actions and all possible outcomes for those actions. So here you can see the 2 branching two branching places. So the first, we consider all the possible actions under policy pi when we transition from the state S, and we kind of average over all those possible actions. And also we consider all the possible transitions, so all the possible next states associated with state action pair SA, right? And we consider all the possible next states. And again, in temporal difference TD0 approach, we are just considering the particular reward and next state associated with particular action. Okay, and if we are trying to estimate the optimal policy, shown here as V star, then our update would be, we will take the maximum over all possible actions, right? So instead of considering all the actions, the optimal policy is the policy that results, so that is the maximizing action, right? Okay, and here, when we are trying to evaluate the action value function instead of just state value function, in a case of sample updates, we get SARSA here, and in a case of dynamic programming, which uses expected updates, we get just a Q policy evaluation. So we will consider state action pair and all possible rewards associated with that state action pair. And then we will consider all the possible next states associated with that, with those possible transitions. And then we will consider all the possible actions, all the possible actions associated with the next state. And that is what we done when doing dynamic programming. And for the optimal policy action value function evaluation, we are going to take the maximum over the actions again. And in case of sample updates, we will get the Q learning, right? So we are trying to estimate not the current policy as we do. As you remember that SARSA is on policy method and Q learning is off policy method. And the policy we are trying to estimate is the optimal policy, disregarding of what policy we are following, right? And that what this backup diagram shows. Okay. And there is a DynaAC approach, which we will look further in the book, I guess, which combine, and it uses samples of the value under the current policy, and yeah, so that will combine the sample updates and DynaQueue algorithm, I guess, but we will see when we get to it. Okay, so
yeah, I agree. I think so. They have defined 7 out of 8 cases in which on which it is based on the 3 binary variables. That is the first 2 dimensions where the update state values and action values. And the second dimension was the S was whether they estimate the value for the optimal policy or for an arbitrary given policy. And the third was the expected updates versus the sample updates. So these were the three dimensions onto which this figure 8.6 has been drawn. And yeah, we will see I think so a combination of the DynaAC system and the 13. Yeah.
Yeah, so here the kind of last missing case, right? It is not kind of something actually, so we cannot probably learn. So we did not consider anything when we want to estimate the optimal state value function using samples, right?
Yep.
So
true.
that is why we have a blank place there. Okay, let's have a look. What do we have here? Yeah, so the expected update. Yeah, you can see that it is given as like let me see. So if we are trying to have so the model estimates the dynamic of the environment, and it gives us this pi hat, which is a distribution of the possible rewards and next states given a state and action pair, and the value we want to get for like action value estimate for state SA will be a sum over all possible future states. This would be a weighted sum, and here you can see that this is kind of similar to our expected returns, discounted expected returns plus the reward, and weighted by the transition probabilities, right? And the corresponding sample update is just our kind of Q value update, right? Or Q learning update as we see it usually. And yeah, so that would be kind of expected equivalent of it, but it requires to know this pi hat, which is a distribution of possible next states given a state action pair, right? And it's not always the case that we have this, or we can kind of feasibly use this in computation. Yeah, and here is a comparison of kind of, even if we can access the expected values for the updates, right? Is it always beneficial to use the expected update? And here you can see the number of computations we need to do. Like, so we will compute the maximum over the of an action value function over all possible actions from state S prime, right? So that is a number of computation needed to be done. And here we compare the expected update would be here B is a branching factor, right? And basically the branching factor is, in case of expected updates, we need to spend at least 1B, so do this at least 1B computations, right? Because yeah, here, have a look at the formula. So we sum over B values, right? So if we have a branching factor B, we have B possible outcomes here, and we need to sum over all these B values. And that is why here the expected updates have this kind of step shaped structure, right? So we do not, before we do this 1B computations, we don't have any kind of expected updates, right? We need to compute all the value for all possible branches. And here you see that sample updates for different branching factors. So for example, consider a branching factor of 2, right? And in this case, you can see that it is particularly beneficial to use the expected update over the sample update, because like with branching factor of 2, we can quickly do this, compute the expectation and get the exact value, right? Instead of using samples. And that will have, obviously, the expected update kind of gets us just to the true estimate in one step. But for higher branching factors, we need to spend much more computation to get the expected update, right? And therefore, we get much more samples before we can do like, or in comparable time as we do one expected update. And for branching factor of 10,000, you can see that we kind of are really close to the true expectation here, but we have that like long before we spend this we basically do this 10,000 computations. Okay, so that is something to take into account when you compare the expected updates versus sample updates, right? And obviously the expected updates are expensive computation-wise. Yeah, okay, so here is the exercise, which is where we have a question that yeah, probably, I don't know, should we go into the details of what generated this figure, or everyone kind of is on the track? Because the question is, suppose that instead of the branching is with equal probabilities, suppose that we have a skewed distribution, and B states are much more likely to occur than the most. And would this strengthen or weaken the case of sample updates over expected updates? Okay, so when at least as for my understanding, when the distribution is skewed, the expected updates are much more beneficial in some cases. Like it also depends on how important are those unlikely cases, right? So consider this cliff world example, right? And assume we have, or let's say, for example, let's consider kind of, yeah, let me try to construct the example on the fly. Consider this case when we have when we play a lottery, and for example, we have a lottery that is extremely profitable for us. We can make a bet, like we bet $1 and we get $1 million back, and there is a probability of 1/10,000 of winning, right? And so the bet is extremely profitable. But if we are like we need a lot of samples to get to this real estimate of this extremely profitable bet, right? And in case but if we will compute the expectation, it is trivial. We get like a sum of 1 million multiplied by 1 divided by 10,000 plus 0, like, right? So in all other cases we get 0, and we see that the expectation of such bet is really high, so it's 100, right? But if we will use a sampling method to evaluate this, it will be kind of really we need a lot of samples to get to this to behave correctly, right? So we lose, or yeah, so most of the time we lose $1, right? So not I just messed the example, so it's not 0, but it's 1 over or 999 over 10,000 multiplied by -1. So, but still, the expectation of the bet it is positive, but the kind of our estimate after say 10 samples will be most probably will be -1, right? And if you will act based on that estimate, you will you kind of losing an opportunity, because you don't play the game which has really high expectation. Okay, so that is the case when kind of using expectation is obviously very beneficial. But consider another situation when this highly unlikely cases are not only improbable but also insignificant, right? So we don't care about unlikely cases, like I don't know, say consider like an example when we are working in this wide grid world, and we need to get to the goal state, and sometimes we will kind of stochastically take the action will take us not where we expect, but for example 1 step to the side. But it does not really make that much difference, and in that case I believe the sample updates would be even better, because we will do a lot of updates of the most relevant transitions, right? And we will get like a good estimate of the relevant transitions, but we will not have to spend that much of computation to this like insignificant to updating this insignificant state. So that is my kind of speculation on this question, and yeah, if you have any opinions, please share. Yeah, so that took us kind of a bit long, so let's probably try to go over next couple of sections. So the next one is trajectory sampling. And so the problem we want to discuss here is we consider two ways of distributing the updates, and the updates can be distributed in the dynamic programming. If you remember, we did the sweeps over all the state space, but let me check. Okay. But sometimes it might be not optimal when we have a large task. So here they give an example when we don't have time to complete even a single sweep over all the state space. So in that case, we want to focus our updates on the most relevant states, right? And a way to do that is called a trajectory sampling. So we will sample state transitions and rewards given by the current policy, not like randomly as we done before. So if you remember our DynaQueue algorithm, it took a random state and a random action from our experiences. But when doing a trajectory sampling, we will use a distribution to distribution under our current policy to get to do the update. Yeah, and they make a point that it's actually hard to imagine any other kind of efficient way to generate the updates other than trajectory sampling, right? And actually, so here, let's consider this example. And example is given as follows. We have a random, let's call it like Markovian process, and we generate 1,000 states, and each state has associated value, which is sampled from a Gaussian distribution with mean 0 and variance 1. And from each state, we can we have we can take two actions, and each action has B possible next state, where B is a branching factor. And we are acting according to the epsilon greedy policy here, with epsilon equal to 0.1. And we are trying to estimate the value of the state under a greedy policy. And there are two ways to do it. So the first one would be a uniform sampling, and that can be done just by randomly iterate, not randomly, but consecutively iterating over all the states, right? And updating those states just as done in say, dynamic programming, right? And another way would be to sample an actions according to the our current greedy policy and update the and yeah, so we will just like follow these trajectories generated by our policy and update the states on the trajectory, right? So that is why the name trajectory sampling. And here we compare the value estimate. We have our kind of number here. We consider the number of expected updates, and we take expected updates here because our termination is not deterministic but stochastic in this experiment. So each transition with some probability leads us to the terminal state, and here the probability was set to 0.1. And that is why we have some expected. We don't have a deterministic length of the episode, but we have an expected length of an episode, which is 10. You know, the expected number of the transitions under this kind of a distribution would be 10, right? And yeah, so the uniform sampling does this sweeps over all episodes, and the on policy sampling, it kind of follows the generated trajectories, and you can see that the on policy behaves much better in the beginning, but it converges to the to some kind of the not suboptimal value estimate. And I would guess this is probably due to the fact that we are following the epsilon greedy policy, right? Not a greedy policy. And the uniform sampling, it just gets us the estimate of a true value for the state, as in dynamic programming, right? But yeah, you can see that the more stochasticity we get, the higher the difference between the like final estimate of the uniform sampling and this on policy sampling. And the higher branching factor, the less kind of benefit we get when comparing the on policy in the beginning, right? So we kind of, you see that these intersections happen earlier when the branching factor is higher. And then we consider the larger experiment. So the setting is the same, but instead of having 1,000 states, we have 10,000 states. And in this case, you can see that even in 200,000 expected updates, the uniform sampling just got to the actual value here, right? And yeah, and the on policy gave us kind of more benefit in this case compared to the uniform updates. So yeah, that is something interesting here. And yeah, probably we got to wrap up now, and we will start with this probably with exercises here, and then proceed with real-time dynamic programming, yeah, in the next session. So we will need another session to summarize this chapter, and we will, so here we will get to not only summarize the chapter, but summarize the part of the book. And yeah, I think we will we should spend another session on this, right?
Yep, that sounds about right. Yeah, we should do a session there too. Or should we club the summarization and the part of the chapter next time for next time?
Yeah, I think that some of these sections would be quite short.
Yep.
So
But
probably we will have enough time to cover both summary and to finish the chapter and cover the summary, hopefully.
yeah, hopefully, yep.
But yeah,
Because
if not,
some of the
we
parts,
can
yeah,
always make it another session. So
yeah, because the next part is interesting with respect to the real world application and the rollouts and how MCTS is being applied in the current online world. If we go about in the depths of how Go is currently being solved by Monte Carlo tree search.
yeah, I think
Uh,
that we will have like it will be really useful for us because that is actively applied in the state of the art right now, right? The Monte Carlo
yep.
tree search. So I think that's what, for example, DeepMind used in their algorithms.
AlphaGo. Yeah.
Yeah.
Alpha
So
series.
yeah, I think we should spend a fair amount of time on it and yeah, have a good understanding. But on the other hand, it kind of introduced here on the high level, and hopefully we will get into more details on that later in the book. I think that these concepts will be revisited multiple times when we will get to the approximate method and so on. So, okay, with that, thank you everyone for attending, and yeah, I hope to see you next time. We will probably yeah, finish this chapter and maybe look at some implementations and examples to like have a better feeling of how everything works. Okay, so see you next Sunday.
Yep. Thanks, everyone.
Doctor.